All right, we're going to look at integrals a little bit more in our next section on page 389. And we've been dealing a lot with integrals in terms of like area under the curve. We've been doing those Riemann sums. We've been doing the antiderivatives, like working backwards. What we're really going to start to get into, though, is how we can use integrals in an applied scenario. The only way we've really done that so far is with the particle motion, like how we can do the area or the integral of velocity, and that would represent something about position. But we can use integrals in other scenarios and not just particle motion. So we're going to take a look at that a little bit today. The first one we're going to take a look at is this kind of scenario paragraph up top. It says, if water is being drained from a swimming pool, and we want the equation R of t to represent the amount of water measured in cubic feet at any given time, measured in hours, then we know that R prime, meaning the derivative, would represent the rate at which that amount of water is changing. So we've done a lot with derivatives. We know derivatives means a rate of change. So if you were to take the derivative of some amount, your value would represent the rate at which that amount is changing. Can we think about what the units would be on this derivative function? If it represents the rate at which the amount of water is changing. Cubic feet per hour. Good. Remember, if it's a rate, we're normally going to have a fractional unit, aka a slope. Now, what we're going to try to do is work backwards. So if we were to integrate this rate, okay, this foot cubed per hour, then that would represent the amount of change, in this case, in water. So mathematically, we can set up an integral equation, which would show the integral of r prime, meaning the derivative, and we know if we work backwards from r prime, we would get the original function r, and we can use that fundamental theorem of calculus where we plug in the top bound minus what we plug in the bottom bound. So notice how on this side, this would represent the area under the derivative graph. What does the right-hand side represent? I'm going to try to write that over here. Can you think about what R of B minus R of A symbolizes? What do you think, Nish?
The difference in cubic feet between like time B and time A.
And time A. Okay, so up here we said that the original function represented the amount of water. So if you take the amount of water at time B and you subtract the amount of water at time A, that's going to give you the difference, aka the change in water amount or water volume. So change or difference in water amount. Okay, and notice how based off the equation, these two things are equal. They are exactly the same. So depending on the information we have, we either have to analyze area under a curve or we have to analyze the change in some amount. Okay, we're going to take a look at kind of the differences between the two and which piece we use depending on the information we have. Okay, so towards the beginning of the year, we were working a lot with derivatives, which means a rate of change. Now we're kind of working backwards using an integral, so that's representing an amount of change. Okay, two different scenarios. They're kind of confusing because they both involve change. It's the type of change that's different. Is it a rate of change or an amount of change? All right, let's check out another scenario. The table below represents velocity, so we're bringing this back to particle motion, where t is measured in minutes. All right, so we don't have a particular graph of velocity, but we just have a table. So for part A, we want to approximate the value of this derivative using a midpoint Riemann sum. Using correct units, explain what it means. How can we perhaps break up this table so that we can use midpoints? You see, Danush?
From 0 to 10, 10 to 20, 20 to 30.
All right, so if you're going to use a midpoint, you would have to span at least 3 blocks. That way you have one in the middle. I guess your next option would be 5 blocks so that you can use the one in the middle, but we don't have enough blocks to do 5 and 5. So we'd have to break it up into 3. So can we estimate this integral value using a midpoint? We have 3 sections, so we're going to need 3 area calculations. Can we list the base and the height for this first rectangle? 10's the base, okay. 1.6 the height, good. All right, so for the next one, it'd be another 10, 3.1, and then another 10, and 1.6. Oh, you already got it? Look at that. Oh, I guess you can just move decimals. So 16 plus 31 plus another 16. 63. All right. I didn't mean to put the unit in there. All right. Can we put a unit and describe what it means in this scenario? Okay. It's going to be feet. Okay. Why is it feet, though? Why is it not feet per minute or feet per minute squared? Okay, so if we work backwards from velocity, this 63 is going to tell us something about position. Now, this is not your position at some point in time, because notice how this interval spanned, or this integral spanned an interval from 0 to 30. So this is not a location. What does this represent? Displacement, aka change in position. So when you are finding an integral value, the number itself can mean 2 things. It either means the area under the function graph, or the amount of change in the antiderivative, the previous function. All right, so this is an approximation for the area under velocity, which means it can also represent the change in position, aka displacement. I like it. Okay, let's try the next one. What is the value from 5 to 25 of acceleration? So we have to think about what we have, what we're trying to find. They give us a table of velocity, and they want us to integrate acceleration. Yeah?
You do v of 25 minus v of 5.
There we go. So we know that velocity is the antiderivative, the previous function to acceleration. So we can do the top bound minus the bottom bound. V of 25 is 1.6, and v of 5 is also 1.6, so we get 0. Good. Can we do units? Feet per minute. Okay, so we started with acceleration, which would be feet per minute squared, and then we worked backwards to velocity, which would be feet per minute. Okay, so what is this 0 foot per minute representing?
Velocity.
Something about velocity. change in velocity on this interval. Okay, notice how at time 5, 1.6 times 20, or time 25 also 1.6, the change is 0 because they're exactly the same. So change in velocity on the interval. Okay, now this is what's confusing because at the beginning of the year when we were doing derivatives, it was always at one point in time, like the velocity at that time, the acceleration at that time, the position at that time. When you're doing an integral, you're doing an interval, okay, a span of time. So that's going to be a change in something. It's not a particular value at a particular spot. Okay, we have to be kind of cognizant of those differences. All right. Let's check out another one. The temperature of water in a bathtub at time t is modeled by a strictly increasing, okay, so only going up, twice differentiable. What does that mean?
You take
Two derivatives.
and it means it's continuous.
Continuous twice. Okay, so that means w of t, the original function is continuous, but also w prime is continuous. And we're measured in Fahrenheit and times measured in minutes. Okay, so we have a table that represents temperature values in Fahrenheit. Using the table, estimate the value of w prime at 12. So how can we estimate a derivative from this original function table at time 12?
Take the slope of points around 12.
Points around 12. Okay, so we'll do 9 and 15. So w prime of 12 is approximately, squiggle squiggle, slope between those 2 points. So we'll do change in y's over change in x's. One point 0166. All right, can you chop it at 6 or round it to 7?
We're trunking it.
We'll chop it or trunk it at 6.
Okay. I like trunking.
Can we put a unit on that?
That right there is going to be degrees Fahrenheit. Per minute.
Per minute. Okay, it's a derivative, it's a rate, so we need a fractional unit. Okay, so what is this 1.0166 number telling us based off this scenario?
The change.
The something change, the rate of change of what? What's changing? Temperature. Good. Of temperature at time 12. So if it's the rate of change of temperature, notice how the derivative value is positive, so temperature would be increasing. Seems to make sense since they told us it was a strictly increasing function. All right, let's try an integral. Evaluate the integral from 0 to 20 of w prime All right, so they're asking us to start with w prime, but notice how the table they give us is w.
So what we're going to do,
Mm-hmm.
we're going to do W20 minus W0.
W20 minus W0. All right, so based on the table, 71 minus 55,
Get 16.
get 16. Unit,
Degrees Fahrenheit.
degrees Fahrenheit. Okay, so what is this 16 representing in the scenario?
A change in temperature.
change in temperature on the interval from 0 to 20. Looks good. So if we're dealing with a derivative, it's a rate. If we're dealing with an integral, it's a change in something. You okay? All right, let's try the last one. For the interval 20 to 25, the function W models the water temperature and has a first derivative given by this very complicated function. Based on the model, what is the temperature of the water at time 25? So notice how they're kind of asking us to predict information. The table at the top only goes to time 20, but they want us to figure out a temperature at time 25.
Well,
And they want us to use this derivative model to help us with that.
I think it's going to be greater than 71.
Right? Because it's strictly increasing,
Yep.
so it's going to go up.
Yep.
So that's one way we can check our work.
So you gotta take the antiderivative of that, then plug 25 in.
There we go. If we were to integrate W prime, we know we would get W at some value minus W at another value.
Yep.
The question is, what are the values we're going to use?
25's gotta be part of it.
25's got to be part of it.
W25 minus W20.
Why 20?
Because it's on you.
It's on the interval, okay? And notice how they tell us that this derivative function is correct or applicable on the interval from 20 to 25. Now, 20 is also probably a good strategic point to use because that's the last point we have available to us in the table. All right, so the integral of this function is equal to W25, which is what we're trying to find, minus W of 20, which we know from the table is 71. How can we figure out what's on this left-hand side?
You're on your calculator.
We're gonna-
find the area under the curve.
We're going to type it in. Yep.
Heck yeah, bro.
Let's go.
All right, so we'll hit math. We can do option 9 to type in our integral. Lower bound 20, upper bound 25, and we're going to type in that very complicated derivative function that they give us. I know it's T's on your paper, but
We'll make it X.
exactly.
Heck
No
yeah.
big deal, just a big deal.
I can't.
Also, make sure you're in radian mode because we're dealing with
What
trig.
is the square root button? X. Day of X.
Now, if you guys wanted to do a graphical approach, you could have graphed this function and then use the integral command on that graphing screen. You know how it shaded it for us? Yeah, you could do that if you wanted to. But let's go ahead and use this number. Now, we only round our final answer to 4 decimal places, but clearly this is not our final answer, so you should probably use a little bit more than that, like 5 or 6 decimal spots. So 2.04315. All right, so to solve for the temperature at time 25, we can just add the 71 over. So 73.04315 degrees Fahrenheit. All right, so Cole, you were right. It was bigger than 71.
Let's go.
We doing okay so far? All right. Let's check out another scenario. A pan of biscuits is removed from an oven, at which point in time 0 is measured in minutes. The temperature of the biscuits is 100 degrees Celsius. The rate at which temperature is changing is modeled by this B prime function. can we perhaps list what the original B of t function represented? If this function is the rate at which temperature changes, what did the original function give us? Just temperature. All right. Find the value b prime of 3. We can do that. Using correct units, explain what it means. What are we going to do? Plug her in. They give us the b prime equation. We'll just plug in 3.
No, that's not the right answer.
Any luck?
Not yet.
No? Okay. I think it's going to be negative.
Negative 8.
Negative 8 point.
3, 6, 3, trunk.
All right. Chop at 3, round to 4, completely up to you. Units. If it came from a derivative.
Something over time.
Temperature, which seemed to be Celsius, over time, which was minutes. Okay? So what is this negative 8 number representing in this context of these biscuits?
The rate of change of the temperature.
Rate of change of temperature, or in temperature, at time 3. Can we say if temperature is increasing or decreasing?
Decreasing.
Because?
The derivative is negative.
Derivative is negative.
Cool.
All right, sketch the graph of b prime of t on the axis below. Explain in the context of the problem why the graph makes sense. All right, so on our calculator, we'll go to y equals, we can clear out anything that's in there, and we'll type in the function they give us. Before I hit graph, I'm going to go ahead and hit the window button and make it the same as what's on my paper. So negative 1 to 11, counting by ones, and then negative 6 to 2, counting by ones. All right, so it looks like we just have this little chunk towards the bottom right-hand side. I'm going to try to be as accurate as possible. So to get some data points, I'm going to hit the trace button. And you can type in any x value you want. So let's see, if I type in 4, I'm almost negative 7, which is kind of off my chart here, but maybe I'll plot it anyway. And then we'll do 5. Maybe I'll jump to 8, negative 3.5-ish. And 11, about negative 2. All right, so general shape, something like that. Can we think about why this graph of the derivative makes sense for this biscuit scenario? Oh, okay, so biscuits are cooling because we took them, it says they were removed from the oven. So biscuits are cooling. So what does that mean?
Temperature is increasing.
They're cooling.
Decreasing.
So temp is decreasing, which means
What's it mean?
which means the derivative
Means something equal.
should be negative the whole the whole time. Okay, they're always cooling, at least until they reach room temperature, right? But if they're always cooling the whole time. So notice how this graph of the derivative, isn't it always negative underneath the x-axis?
I want some turkey.
Looks good. Turkey and biscuits. Yep. All right. Last one. At time t equals 10, what is the temperature of the biscuits? If we think about the information, they give us the equation for B prime, and they're asking us about a temperature.
Well, do B prime of 10. Never mind.
All right. If they give us a derivative, we're gonna have to work backwards to represent the B of t original equation, which we said was temperature. So if we work backwards from the derivative, we'll get B of something minus another B of something. Can we figure out what those somethings should be? Y 0, Y 10. Right. We know 0 from the top, and 10 is what we're trying to find. So 0 to 10 we'll use as our bounds. B of 10, we're trying to figure that out. What was B of 0? 100. Okay. How can we figure out this left-hand side? Calculator. We're going to type it in. All right. Actually, let's go back to the graph. Okay, we already have the graph listed. So I'm going to go ahead and do second trace. We can choose option 7. And I'll pick a lower limit or a lower bound of 0. And then an upper bound of 10. And it's going to shade all that in for me. So we get negative 65.81725. All right, so to get our B of 10 value, we'll add over 100. $34.18275 units, degrees Celsius. There we go. We starting to feel a little bit more comfortable with derivative, or not derivatives, integrals? Okay, it's the amount of change. We'll save the last one for tomorrow.
No.